You know, people ask me all the time on Feynman, what's the most mind-bending idea in all of physics? And I always have to stop and think because there are so many wonderful candidates. But if I had to pick one that really sits with you, that follows you home and keeps you up at night staring at the ceiling, it's this question of dimensions. Now you think you know what a dimension is. You live in 3 of them. You walk forward and backward. That's 1. You walk left and right, and that's 2. You go up and down, that's 3. Simple, done, good night. But what if it isn't done? What if there are more directions? Directions you've never moved in, never felt, never even suspected. And they're right here, folded up so small that your entire body passes through them 1 trillion times a second without you ever noticing. That's not science fiction. That's a serious, honest, mathematical possibility that physicists have been wrestling with for over a century. And today I want to sit down with you and really think about it, and the way I like to think about things, from the bottom, with no nonsense, no hand-waving, just the real ideas laid out carefully so that by the end of this you actually understand what extra dimensions mean. Not just the words, the meaning. Let's start at the beginning, because the beginning is always the honest place to start. What is a dimension, really? When a mathematician or a physicist uses that word, what are they actually saying? A dimension is simply a direction of freedom, a direction in which something can move or change independently of all the other directions. Think about an ant walking on a tightrope. That ant lives in a one-dimensional world. It can go forward, it can go backward, that's it. It has 1 degree of freedom, 1 dimension. Now put that ant on a table. Suddenly it can go forward, backward, left, right. 2 dimensions, 2 independent directions of movement. Now let the ant fly through the air, up, down, in every direction. 3 dimensions. Each time we added a dimension, we added a new direction that was completely independent of the ones that came before it. You can't make up by combining forward and sideways. They're genuinely separate. So the question becomes, is 3 the end? Is there some deep law of nature that says 3 and no more? Or is 3 just what we happen to notice? And that second possibility is the interesting one. Now here's where it gets subtle. And I want you to follow this carefully because it's the key to the whole thing. Just because you can't see something doesn't mean it isn't there. That sounds obvious when I say it, but we forget it constantly. Imagine a garden hose. You're looking at it from very far away, from an airplane, say. What does it look like? It looks like a line, a one-dimensional object stretching across your garden. You'd say, that hose has 1 dimension. It goes from one end to the other. But now walk up to the hose, get close to it, wrap your hand around it. Suddenly you see it isn't just a line at all. It has a circle going around it. It has thickness. There's a second dimension, the one that goes around the circumference of the hose, that was completely invisible to you when you were far away. And here's the thing. If you were a tiny creature small enough to live on the surface of that hose, you'd know about both dimensions. You could walk along the length of the hose, or you could walk around it in a circle. 2 very different directions, 2 dimensions. But an observer far away, they'd only see 1. This is exactly what physicists mean when they talk about extra dimensions that are compactified or curled up. The idea is that there might be extra directions of space, but they're curled into circles so tiny that no experiment we've ever done has been able to detect them. How small? Well, the scale people often talk about is something called the Planck length, about 10 to the minus 35 meters. That's so fantastically small that compared to it, a proton is like comparing a proton to the entire observable universe. We have absolutely no tools that can probe distances that small directly. So the extra dimensions could be right there at every single point in the space around you, and you'd never know. Now, who first started thinking this way? Where did the idea come from? The first serious attempt was made by a mathematician named Theodore Kaluza in 1919. He did something audacious. He took Einstein's theory of general relativity, the beautiful theory where gravity is the curvature of space and time. And he said, what if I just add 1 more dimension? What if space-time isn't 4-dimensional but 5-dimensional? And he worked out the mathematics, and something remarkable happened. When he added that 5th dimension and worked out the equations, out popped not just Einstein's equations for gravity, but also Maxwell's equations for electromagnetism. Electricity and magnetism came tumbling out of pure geometry. Think about what that means. 2 completely different forces of nature. Gravity, which pulls you toward the earth, and electromagnetism, which makes light, which powers your nerves, which holds atoms together. Both of them described as nothing more than the curvature and shape of a five-dimensional space. It was breathtaking. Einstein himself read Kaluza's paper and was stunned. He held on to it for 2 years before he would even forward it for publication because he kept thinking, this can't be right. It's too beautiful. But there was a problem. Where is this fifth dimension? Why can't we move in it? Why don't we see it? That's where a Swedish physicist named Oskar Klein came in 1926. Klein provided the answer that became the template for all future extra dimension theories. He said, the fifth dimension is there, but it's compactified. It's rolled up into a circle, and that circle is unimaginably small, roughly at the Planck scale. So at every point in what we call ordinary four-dimensional space-time, there's actually a tiny little circle. A fifth direction you could move in, but only for an absurdly small distance before you come right back to where you started. This is called Kaluza-Klein theory, and it was the first serious scientific proposal of hidden extra dimensions. Now let me tell you why this idea didn't just stay as a beautiful curiosity, but became central to modern physics. The problem we have in physics, and when I say we, because this is very much an ongoing problem, it was a problem in my time and it remains one, is unification. We have general relativity. It describes gravity magnificently. The bending of light around stars, the slowing of time near massive objects, the expansion of the universe, black holes, all of it comes out of general relativity with extraordinary precision. And then we have quantum mechanics, which describes everything else. Atoms, electrons, photons, the strong force inside atomic nuclei, the weak force that causes radioactive decay. Quantum mechanics is also spectacularly successful, but these two theories don't fit together. When you try to combine them, when you try to write down a quantum theory of gravity, you get nonsense. You get infinities that can't be removed. The mathematics breaks down. This is deeply unsatisfying. Nature isn't divided into quantum stuff and gravity stuff. Nature is one thing. There should be one description. And the leading candidate for that unified description, the framework that most theoretical physicists have invested the most effort in, is string theory. And string theory requires extra dimensions. It doesn't suggest them as a possibility. It demands them. Let me explain why. In string theory, the fundamental objects aren't particles, tiny point-like things. Instead, they're strings, unimaginably small loops or strands of energy vibrating at different frequencies. The way it works is like a violin string. When a violin string vibrates, it produces different notes depending on how it vibrates, the fundamental frequency, the harmonics, different vibrational patterns, different sounds. In string theory, different vibrational patterns of the fundamental string produce different particles. An electron is the string vibrating one way. A photon is it vibrating another way. A graviton, the particle that carries gravity, is another vibrational mode. Now it turns out that when you work out the mathematics of these vibrating strings carefully, when you demand that the theory be consistent, that it not produce contradictions, that probabilities add up to 1 and causality is preserved, the mathematics forces a very specific conclusion about how many dimensions of space are needed. For the most well-developed version of string theory, called superstring theory, the answer is 9 dimensions of space and 1 of time, 10 dimensions total, 9 dimensions of space. We observe 3, so 6 of them must be hidden, compactified, curled up in some small but intricate shape. There's a later extension called M-theory, proposed by Edward Witten in 1995, which unifies the 5 different versions of string theory that had been developed. M-theory requires 10 dimensions of space and 1 of time, 11 total. These aren't arbitrary numbers pulled from the air. They come directly from requiring mathematical consistency. The theory tells you how many dimensions it needs. Now, the shape of those hidden dimensions turns out to matter enormously, and this is one of the most fascinating parts of the story. The 6 hidden dimensions in superstring theory are compactified, but they're not compactified into simple circles. They're compactified into complicated geometrical shapes called Calabi-Yau manifolds. What's a Calabi-Yau manifold? Well, it's hard to visualize because it exists in 6 dimensions, and our brains evolved to navigate 3. But the essential point is that it's a very specific type of curved, compact space, and the particular shape of the Calabi-Yau space determines the physics you get. Different shapes of Calabi-Yau manifold give you different numbers of particle types, different masses, different force strengths. In principle, The specific Calabi-Yau shape our universe has compactified into would explain why the electron has the mass it has, why the strong force has the strength it has, why there are 3 generations of quarks and leptons, the constants of nature, these numbers we measure experimentally and just accept without explanation, might actually be geometric features of the hidden dimensions. That's an extraordinary possibility. The mass of the electron isn't just a number someone wrote down. It's a geometric property of 6-dimensional space you can't see. Now, I should be honest with you here because I've always believed that honesty in science is the most important thing. String theory, despite its mathematical elegance, despite the fact that it requires extra dimensions in a way that seems to give us hope for unification, is not experimentally confirmed. We don't have direct evidence for it. We don't have direct evidence for extra dimensions, period. What we have are theoretical arguments, mathematical consistency requirements, and indirect hints, but not proof. And I've always said, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If the theory disagrees with experiment, it's wrong. That's the game. That's science. So the question is, could we ever detect extra dimensions? Is there any experimental signature we might look for? And the answer is yes, there are several ideas. The first idea involves gravity. Here's something interesting. We've tested the other forces of nature at incredibly tiny distances. Quantum electrodynamics has been tested to extraordinary precision. But gravity? Gravity is so weak at small distances that testing it directly is very hard. Newton's law of gravity says the force falls off as 1 over the distance squared, that the inverse square law. We know this works at astronomical distances, and we've tested it down to about 1/10 of a millimeter. Below that, we have very little direct experimental data. Now, here's the key point. If there are extra dimensions, gravity might behave differently at short distances. In ordinary 3-dimensional space, the inverse square law comes from the fact that the gravitational field spreads out over a sphere, and a sphere's surface area grows as the square of the radius. That's where the squared in inverse square comes from. But if there are extra dimensions, even if they're compact, at distances comparable to the size of those extra dimensions, gravity starts spreading into them too. And the force law changes. If there are 2 extra compact dimensions, gravity at very short distances would fall off as 1 over distance to the 4th power, not the 2nd. Some theoretical proposals, particularly models developed by Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali, sometimes called the ADD model, even suggested that extra dimensions might be as large as a fraction of a millimeter. Not at the Planck scale, but actually large enough to be tested by tabletop gravity experiments. These experiments have been done. They've been refined over the years, and so far they haven't found any deviation from the inverse square law. But the search continues and the bounds get tighter. The second experimental avenue involves particle colliders, machines like the Large Hadron Collider at CERN, which smashes protons together at enormous energies. If extra dimensions exist, even at tiny scales, the collisions in these machines might produce what are called Kaluza-Klein excitations, essentially particles that are like the ordinary particles we know, but with extra energy from their motion in the hidden dimensions. They'd show up as heavier copies of familiar particles. There's also a more dramatic possibility. If extra dimensions exist and are large enough, the LHC might be able to produce tiny microscopic black holes, objects that would quickly evaporate by radiating particles. The signature would be very distinctive. Physicists have searched for these. None have been found yet. But again, the search continues, and the energies achievable will increase with future machines. The third avenue is more subtle, and it comes from the early universe. If extra dimensions exist, they would have influenced how the universe evolved in its first moments. The cosmic microwave background of the faint glow of radiation left over from the Big Bang, which we can map in exquisite detail, carries a record of the early universe's physics. The precise pattern of tiny temperature fluctuations in the CMB might contain signatures of extra dimensions. This is being studied carefully. Now let me come at this from a completely different direction, because I think there's another way to appreciate why the idea of extra dimensions is not as crazy as it sounds, and that's through the history of dimensions in physics more broadly. Every time we've expanded our conception of the dimensionality of nature, we've gained enormous power. Here's a beautiful example. In the 19th century, people began to realize that you could think of the state of a mechanical system, say a gas made of 1 trillion molecules, as a single point moving through an abstract phase space with a huge number of dimensions. Each molecule has 3 position coordinates and 3 velocity coordinates. So the full gas has something like 6 trillion dimensions of phase space. This is purely abstract. Nobody thinks this phase space is real in the way the room you're sitting in is real. But by working in this high-dimensional abstract space, an entire field, statistical mechanics, became tractable. The mathematics of high-dimensional spaces gave us thermodynamics. Similarly, in quantum mechanics, the state of a particle is a vector in an infinite-dimensional Hilbert space. Again, this seems wildly abstract, but it's the mathematics that works. So physicists have a long and productive history of finding that nature is best described in more dimensions than the ones we walk around in. Whether those dimensions are purely mathematical tools or whether they correspond to physical directions in which things actually move, that's a deep question, one that we don't have a final answer to. There's another development I want to tell you about that I find particularly beautiful. It's called the holographic principle, and it's related to extra dimensions in a surprising way. In the 1990s, theoretical physicists Jacob Bekenstein, Stephen Hawking, Gerard 't Hooft, Leonard Susskind discovered something astonishing about black holes. The amount of information that can be stored inside a region of space is not proportional to the volume of that region, as you might expect. It's proportional to the surface area, the two-dimensional boundary around it. This is the holographic principle. It says, in a precise mathematical sense, that a three-dimensional region of space can be completely described by information living on its two-dimensional boundary, like a hologram, where a three-dimensional image is encoded on a two-dimensional surface. In 1997, Juan Maldacena took this further with what's called the AD-S-CFT correspondence, one of the most important discoveries in theoretical physics in the last 30 years. He showed that a specific theory of gravity in a five-dimensional curved space called anti-de Sitter space is mathematically equivalent to a specific quantum field theory living on the four-dimensional boundary of that space. These two theories, one in 5 dimensions with gravity, one in 4 dimensions without gravity, give identical predictions for all observables. They're two descriptions of exactly the same physical reality. This is profound. It suggests that dimensions themselves might not be fundamental. The distinction between living in 5 dimensions and living in 4 dimensions might be a matter of description, not a fact about nature. Now that should make you stop and reconsider everything. Let me step back and think about what all of this actually tells us about reality. When I was young, I had a certain picture of what a physicist's job was. You go out, you look at nature. Nature gives you data, you build a model that fits the data, and you move on to the next thing. Reality is what it is. Your job is to describe it accurately. But the deeper you go, the more the line between description and reality starts to blur. Are the extra dimensions in string theory real extra dimensions, directions you could actually move in if you were small enough? Or are they mathematical scaffolding, tools that make the equations work out, but not corresponding to anything physical? The honest answer is, I don't know. Nobody knows. What I can tell you is that mathematics has an extraordinary track record of turning out to be physically real. When Dirac's equation produced negative energy solutions, he could have thrown them away as mathematical artifacts. Instead, he predicted the existence of antimatter. 4 years later, Carl Anderson found the positron in cosmic rays. When general relativity predicted that light would bend around massive objects, Einstein could have said, well, it's just a mathematical quirk of the geometry. Instead, Eddington measured the deflection in 1919 and it matched exactly. Mathematical structures that appear in physical theories have a strong tendency to turn out to be real. So when string theory's mathematics insists on 10 or 11 dimensions, I think we should take that seriously. Not as proven fact. We shouldn't do that. But as a genuine possibility worth pursuing, honestly. There's a question I know you're wondering about. If there are extra dimensions, what are they like? What would it mean to experience them? We can't experience them directly. They're too small, but we can reason about them. Think about it this way. Every point in the space around you, the point right in front of your nose, the point a meter away, every point, if extra dimensions exist, each of those points is actually a small extended structure. A tiny 6-dimensional curled up space, like a microscopic Calabi-Yau manifold sitting at every point. The air isn't just three-dimensional, it's nine-dimensional, but 6 of those dimensions are coiled up at a scale of 10 to the minus 35 meters. Objects that we think of as points, electrons, quarks, might actually be extended objects when viewed at those tiny scales. Strings, as string theory proposes, stretching and vibrating through the full nine-dimensional space. The forces between particles, the ways they push and pull each other, arise from the geometry of this nine-dimensional space, just as gravity arises from the curvature of four-dimensional space-time in Einstein's theory. In a sense, if the string theorists are right, everything, every force, every particle, every interaction is just geometry. The universe is nothing but shape in 9 dimensions of space and 1 of time. Now let me tell you about one more idea that I find especially thought-provoking. It's called the brain world scenario, and it was developed seriously in the late 1990s by Lisa Randall, Raman Sundram, and others. In string theory, in addition to strings, one-dimensional objects, there can be higher dimensional objects called brains. A two-dimensional brain is like a membrane, a sheet. A three-dimensional brain is like a thick slab of space. The brain world idea proposes that our entire universe, everything we see, every galaxy, every atom, you, me, all of it, lives on a three-dimensional brain floating in a higher dimensional space called the bulk. We're stuck to this brain. The particles that make up matter, the electromagnetic force, the strong and weak nuclear forces, they all live on the brain. They can't escape into the bulk. They're confined to our three-dimensional surface. But gravity is different. Gravity in this picture can leak into the bulk. Gravity can propagate through the extra dimensions. This is actually one reason gravity is so much weaker than the other forces. Think about it. Gravity is extraordinarily weak compared to electromagnetism. The gravitational force between a proton and an electron is about 10 to the power of 39 times weaker than the electromagnetic force between them. That's an enormous number. Why should there be such a fantastically large ratio? The brain world scenario offers an answer. Gravity isn't intrinsically weak. It seems weak because it's spreading into extra dimensions that the other forces can't access. Gravity is being diluted across a larger space. The other forces are concentrated on our brain. If this is right, then gravity at very short distances, before it has had a chance to spread far into the extra dimensions, should be much stronger than Newton's law predicts. Experiments are testing this. I want to talk about something that I find philosophically fascinating here, the question of why space has the number of dimensions it has. In 3 spatial dimensions, you can have stable orbits. A planet can go around a star in a nice ellipse, and if you perturb it slightly, it stays in an orbit. This is a very special property of three-dimensional space. In 4 spatial dimensions, orbits are unstable. Perturb a planet slightly, and it either spirals into the star or flies away. You also need at least 3 dimensions for complex structures. In 1 or 2 dimensions, the possibilities for building complicated networks, like neurons, like the brain, like chemistry, are very limited. And in 3 dimensions, you can have knots. Knots are genuinely three-dimensional things. DNA is knotted. The topology of proteins involves knots. Complex three-dimensional structure is part of what makes life possible. So there's an anthropic argument, a selection effect, for why we find ourselves in a universe with 3 large spatial dimensions. Even if there are 10 or 11 dimensions total, we'd expect to find ourselves in the part of the universe or the configuration of the universe that supports complex observers. Whether this argument is satisfying is a matter of taste. Personally, I always want a deeper answer. I want to know why nature picked this configuration, not just that we couldn't exist to ask the question otherwise, but I acknowledge it's a real argument. Let me come toward the end here, and I want to leave you with the honest state of things. We don't know if extra dimensions exist. We have beautiful, powerful mathematical frameworks, string theory, M theory, Kaluza-Klein theory, brain world scenarios, that suggest they might. We have a deep, persistent problem in physics, the incompatibility of quantum mechanics and general relativity, that extra dimensions might help solve. We have experimental searches underway, testing gravity at short distances, looking for new particles in colliders, scrutinizing the cosmic microwave background. But we don't have the answer yet, and I want to say something about that uncertainty because I think it matters. There's a temptation, both in science and in popular accounts of science, to either oversell the speculation, to say we've almost figured out the theory of everything and it has 10 dimensions, or to dismiss it, to say extra dimensions are just mathematical fantasy with no connection to reality. Both of those are wrong. The honest position is, this is a serious, active area of scientific inquiry. The mathematics is profound and has already generated real insights. The AD-CFT correspondence, for example, has been enormously productive in understanding quantum field theory, even setting aside the question of whether string theory is the right theory of gravity. The experimental program is real and ongoing, and the question, are there more dimensions of space than we can see, is one of the deepest questions in physics. I've always believed that the most exciting phrase in science is not eureka, but that's funny. The moment when you notice something that doesn't quite fit, that puzzles you, that hints there might be more going on than you thought. The fact that gravity is so weak compared to other forces, that's funny. The fact that the mathematics of string theory insists on 10 or 11 dimensions, that's funny. The fact that the holographic principle tells us a volume of space can be described by information on its boundary, that's funny. These things might be clues. They might be pointing toward a deeper reality. A reality in which the space we live in is vastly richer than it appears, in which every point around you harbors hidden dimensions, curled up and waiting to be found. Or they might be beautiful mathematical structures that nature chose not to use. Either way, the search is worth doing. The universe doesn't owe us simplicity. It doesn't owe us 3 dimensions and no more. And if it turns out that the truth is stranger and richer than we imagined, well, that's always been the lesson of physics, hasn't it? Every time we looked more carefully, there was more there than we expected. I expect this time will be no different. Thank you.